In this video, we are going to look at metallic bonding. So we are going to basically look at metals. That's where the name comes from. So all metals, apart from mercury, are actually solid at room temperature. Name it copper, iron, sodium, potassium, they are all solids with the exception of mercury. Except mercury, which is a liquid at room temperature. So we are going to see how these metals actually have their own bond, how the atoms within themselves can form a certain kind of chemical bonding. So this is going to be our third type of bonding. After having looked at ionic bonding, covalent bonding, now let's look at metallic bonding. When you look at metal atoms, we shall believe that the force that keeps metal atoms together is going to be called metallic bond. Hopefully we believe it soon. And one thing to note is that we have somehow separated metallic bond from the other two types of bonding. It's neither a covalent bond nor an ionic bond. Remember, an ionic bond, we had transfer of electrons from the metal to the non-metal. Transfer of electrons. However, under covalent bond, basically this was sharing of electrons between non-metals. So this is sharing of electrons. However, we are going to see how the metallic bond differs from these, although it might also look similar to one of them. However, we put it separate from these two types of bonding because the properties that arise cannot be explained by covalent bonding or ionic bonding. For example, metals are very good conductors of electricity in solid state. Moreover, remember, for ionic bonding or ionic compounds, they could only conduct electricity in solution or when molten. But for metals, they can conduct electricity in solid state. As we have seen, most metals are solids with the exception of mercury. So because of that, we can't somehow attach metallic bond to one of these two types of bonding, covalent and ionic bonding. Both ionic and covalent compounds cannot do so with the exception of graphite. In our previous video, we had a look at some of the properties of giant atomic structures where we had our graphite, and we basically said graphite can actually conduct electricity, although its bonds are mainly covalent in nature. It can conduct electricity. So with the exception of graphite, ionic and covalent compounds cannot be like the metallic substances that can conduct electricity in solid state. So let's look at the actual metallic bond. Formation of metallic bond. At least we have seen that most metals are actually solids. And if you were to look at the arrangement of atoms in these solids, we shall see that atoms are always closely packed. Although they are vibrating, they are closely packed. And basing on the atomic structure, we know that atoms are generally neutral. They have no charge at all, meaning that the number of protons and the electrons are usually equal. So if this is our structure of, say, sodium at atomic level, different sodium atoms, one after the other, one after the other. So what happens? We know that sodium actually has electronic configuration of 281. So each of these atoms has an extra electron in the outermost energy level. So how does metallic bonding arise or come about? When you look at each metal, its last electrons always have the potential of being delocalized. What do we mean by delocalized? Not being attached to a single atom, not being bonded to only one atom. That is to say, they are mobile, they are free to move around, they are free to roam, free to move. So let us see what we mean by this. If this sodium atom is free to move, what does that mean? When you look at each of these atoms, if this is atom 1, atom 2, atom 3, that means all these 3 atoms, each of them has 1 electron, and then within this very structure, electrons, this electron, and then this other electron, they can actually move around. So let us see what we mean by that. So in this image, we have, let us say this was previously our sodium atom. However, when it loses its 1 electron, this electron now becomes free to move. This 1 electron is this electron in the electronic configuration of sodium. So each of these atoms ends up losing at least its outermost electron. Losing, but it remains within the vicinity of this atom. So when the sodium atom obviously loses the electron, it has to become positively charged. That's why we see the positive charges here. So in metallic bond, what happens is that the outermost electrons of the atoms usually become free to move around. So they're not attached to a given atom. So we can't say that this electron here is fully and only attached to this metal ion here. So the positively charged ion is not also attached to only 1 electron, but this electron is free to move around just like the others. So all these negatively charged electrons you see here are free to move around within this structure of the metal or within these other atoms. So what do we mean by the metallic bond? Whenever the electron is lost, a positive charge is created. So this positive charge, in relation to a negative charge, we know that if you have opposite charges, they will always attract. So opposite charges attract. So positive and negative. So this positive ion is attracted to this negative electron, just like this negative electron is attracted to this positive electron. So that force of attraction between the metal ion, which is positively charged, and the negatively charged free electron, or delocalized. Delocalized is a better word than free because it shows that it's not in a particular place than actually being 100% free. So the force of attraction between the negatively charged metal ion, the positively charged, and the negatively charged electron is what will constitute a metallic bond. It is kind of electrostatic. So a metallic bond is electrostatic in nature. However, it is taking place between similar atoms. This was a previously sodium atom, now a sodium ion, sodium atom, now a sodium ion. So it occurs within the atoms of that metal. So basically that's how a metallic bond is formed, when the metal atoms lose the outermost electrons, and then the electrons will always be attracted by the formed metal ion. So if you look at maybe magnesium, if you look at its structure, that means for it will have 2 delocalized electrons moving around. So that's how a metallic bond is formed. We finally reach our top 3 questions. Question 1. Metallic bond is neither a covalent nor an electrovalent bond. True or false? 2. The force which binds various metal atoms together is called, I think that is self-explanatory. Then lastly, what do we mean by sea of electrons or electron cloud? I didn't talk about this, but I felt it's worth noting in our top 3 questions. Try and find out what we mean by sea of electrons. At least one thing I'm certain, in my previous page, I somehow had it in one of the images. as sea of electrons. It was present right in front of our eyes. So what do we mean by sea of electrons or electron cloud in regard to metallic bonding? Thanks for watching. If you are new or if you find these videos helpful, don't forget to like, share, comment, and most importantly, subscribe so that whenever I upload new content, you are one of the first to be notified. In our next video, we are going to look at properties of metallic bond. This is likely to be our last video under this series. Be well.